Is it okay if we start now, Anupreeta?
Yeah, I'm fine.
You're fine, right? Okay, great. Okay, so I can't see any of the audience. I'm assuming that there is a full room there listening to us. Welcome everyone in this session number 2 on general relativity and cosmology. Our first speaker is Anupreeta More, who is going to talk about gravitational wave sources and gravitational lensing.
Waves and gravitational lensing of gravitational waves. I would like to point out that most of the work that I'm going to present today is done by Anuj Mishra and Sunil Chaudhary, who are PhD students here at IUCA. I've also listed various collaborators on the slide. Moving to the next slide, I hope everyone can see my slide and the pointer. So let me begin with the introduction of gravitational waves. Einstein predicted the existence of gravitational waves more than a century ago. So it was a tremendous achievement when the first direct detection of gravitational waves were made in September 2015. While these gravitational waves originated from merger of binary black hole, there are other kinds of gravitational wave sources expected to be found. For example, from stochastic processes in the early universe, continuous emission from binary or isolated sources, and bursts from hitherto unknown origins. Since the first detection of these in spirals of compact binary coalescence signals that we found, so far we have detected nearly 100 the CBC signals. But the detection of these CBC signals is not really easy, mainly because the data consists of not only the gravitational wave signals, but a lot of transient noises called glitches. So searching for gravitational wave events is like searching for needles in a haystack. For example, I'm showing here a time frequency spectrogram for a gravitational wave event on the top left. On the right-hand side, you can see several examples of different kinds of glitches, blips, whistles, and scattered light. There are many more such categories. Among these different types of glitches, the blips are the ones which are much more similar to the CBC signals. So here is an example where in blue, you can see the real blip present in the data. And then the orange waveform, which is overlaid on it, is for a CBC signal. So you can see there is quite some similarity. And the rate of occurrence of these blip glitches is also very high. Naturally, this affects the search of CBC signals. And to add to the problem, the origin of these blip glitches is still a mystery. There have been several studies which have tried to identify these blip glitches and mitigate them. They have met with some success. But here in this work, I'm going to talk about a slightly different way of analyzing or identifying BBH signals and distinguishing them from the blip glitches by using a slightly different or 2D representation of the gravitational wave data, what we call the sine Gaussian projection maps. And then we generate these sine Gaussian projection maps and analyze them with machine learning algorithm, mainly a convolutional neural network, with the goal of distinguishing the BBH signals from the blips. So the way we generate these sine Gaussian projection maps is by taking, let's say, a signal X and cross-correlating with a sine Gaussian function, which is mainly defined by the width of the this sine Gaussian function and the central frequency. We calculate this cross-correlation by maximizing over the phase of the signal. And then we repeat this calculation for a range of widths shown here on the y-axis and range of central frequencies on the x-axis. As a result, we generate this kind of a 2D representation called the sine Gaussian projection maps. And this particular map here shows a strong projection here on the top left corner for a simulated BBH calculated for one of the LIGO detectors. We do the same thing for another detector. So you can see that the signals look, these projections look very similar in the two detectors for the simulated BBH. This forms our input data to the neural network. Similarly, we calculate these projection maps for real blip glitches taken from the data. So here, this is how the projection looks like for one of the LIGO detectors, and then the corresponding data in another detector looks pretty much noisy. So this forms our bulk of our training sample. We generate several thousands of such images and train the neural network. Next, we assess the performance of our network by using standard metrics like the receiver operating characteristic curves. So here we are showing the plots, we are showing the true positive rate versus the false positive rate. You are also seeing here three or two sets of curves. The thicker solid curves correspond to higher SNR signals in our sample, and the thinner dotted curves represent the lower SNR. The two plots here correspond to two different bins for the total masses of the binaries. This is the lower mass and this is the higher mass. Overall, we find that the blue curves are for our CNN algorithm, and then the orange and the red curves are for other ranking statistics which have been used in the past. And what we find is that the performance of our CNN algorithm is much better than the other methods. So if we pick one false positive rate of, let's say, 0.01 here, then at the same false positive rate, we get much higher true positive rate compared to other methods. So overall, the sigma-net algorithm that we have come up with has a better performance compared to some of the existing methods for identifying the BVH versus blip glitches. We have also calculated another metric, which is called the F1 score. This is a combination of precision and recall. Recall is just the true positive rate, and the precision tells us what fraction of the total detection are the real signals. So this F1 score gets a high value only when both the precision and recall is very high. And this is what we find for our test sample, which is separated as a function of, again, the SNRs and the total masses of the binaries. So we find very high F1 scores, which gives us confidence in our sigma-net algorithm. Here on the right-hand side, I am showing the computation times on a single core. So the times here listed are for various steps in our analysis. We find that the most time-consuming step is the generation of the SGP map, which takes 30 seconds for one SGP map on one core. Of course, we are parallelizing this process and we run on hundreds of cores. So overall, the process is faster, but we want to further look into reducing this time taken for generating each SGP map. Lastly, we test our sigma-net algorithm on the real sample of gravitational wave events. So we have taken the GWTC3 catalog of gravitational wave events. And again, we have split it here as a function of the SNR and the total masses of the binary. And we find that 95% of the real events are correctly identified. Going to the future, we want to include more examples of glitches in our training sample, and also possibly uncategorized noise triggers that are there in the data. And we also want to consider including a wider range in the CBC total masses than we have explored so far. So from now, I want to switch gears and talk about gravitational lensing of gravitational waves. So as an introduction, what we mean by strong gravitational lensing is that you have signals coming from a distant source which are deflected in multiple directions due to a massive galaxy in the line of sight, or a cluster of galaxies. And as a result, what we see from the observer point of view are multiple instances of the same source. In the electromagnetic domain, the gravitational lensing has been observed and being studied for several decades now. Here is an example of a gravitationally lensed quasar where you can see the 4 point-like images of the quasar. And then you can also see a red arc, which is the host of that quasar situated in the background. This is an image taken from the Hubble, and there are many such hundreds of gravitational lenses which have been studied so far. However, the gravitational lensing of gravitational wave sources, even though it has been predicted, we are yet to find any such instances. Let me tell a little bit more about the properties of these gravitationally lensed gravitational wave sources we expect to see in the data. So in typical gravitational lenses, when we see 2 images, we call them double, and when we have 4 images, we call them a quad. So in the context of gravitational waves, since we are mainly looking at the time dimension, the images that we will be seeing, the multiple images that we'll be seeing due to lensing of the same background source, they will be arriving at different times at us. So there will be a time delay between these multiply lensed events. And you can imagine this this arrival time surface in the lens plane. And there are images that are formed at the different stationary points in this arrival time surface. So the images that are formed at the minimum of the time arrival time surface are called the type 1 images, and the ones which are at the saddle points are called the type 2 images. These different types of images also show a phase shift. And lastly, the distances of these lensed events is going to be altered because of the lensing magnification. So the main lensing observables that are relevant for our work are the time delays, the relative magnifications, and the phase differences. Now, the existence of lensed gravitational waves has been predicted, but it's important to calculate the actual lensing rates that we expect to find in the data, and to understand whether we'll be able to detect real gravitational lenses in the ongoing observations in the current observatories. So with that goal in mind, we have calculated the relative lensing rates for 2 different types of lens population, where the lenses are either individual galaxies or the lenses are made of galaxy clusters. And since there is some uncertainty in the models of the merger rate densities for the binary black holes, we have considered different models from the literature, and we have calculated these lensing rates accordingly. Overall, what we find are that the lensing rates are roughly 1 in 1,000. These are similar for galaxies and galaxy clusters, but the galaxy cluster lenses are going to be rarer by a factor of 2 or so. Overall, these lensing rates have some uncertainty because of lack of our understanding of the merger rate density models. So there is a huge error bar on this number. But optimistically speaking, it is possible that in the next couple of years, if we are seeing several hundreds to 1,000 binary black hole events, then we are likely to find a true lensed gravitational wave event. We can also turn this problem around and ask if there are n lensed events that are found, or if there are no lensed events we are finding in our data, then which of the BBH merger rate density models are valid. And this is illustrated by this plot here. We are showing that given that there are no detection of lensed gravitational wave events so far, these red shaded regions are the plausible models for the merger rate densities, and the blue shaded regions are the ones which are excluded. All right, so now moving on to the problem of identifying strong lensing candidates in the data. There have been various methods that have been developed to identify promising lens candidate in the literature. One of them is this posterior overlap analysis. And this relies on the fact that the posterior distributions of the parameters of the binary black hole source, in case of lensing, if there are 2 events which are lensed they will have common parameters, and their posterior distributions will have significant overlap. And so this B overlap captures that aspect. And this is further combined with this R-gal factor, which relies on the fact that if you're considering the population of lensed event pairs, their time delay distributions are going to be different from those of just some random pair of events. So this combined ranking statistic is used for identifying, it's a fast method for identifying these lensed candidates. And in our recent work, what we are proposing is that instead of using R-gal, which just relies on the time delay distribution, it would be much more informative to make use of not only the time delays of a given lensed pair, but also the relative magnifications and the phase differences. Since these are correlated, these observables are correlated, so it would be much more useful to consider something like an M-gal over R-gal. To illustrate this point further, we have generated a mock sample of realistic lenses. So here I'm showing the joint distributions of the relative magnifications and the time delays. In this panel, these are the images, event pairs of same type, and here the event pairs are of different types. So these green contours show the event pairs corresponding to lensing, and you can see that the distribution is well separated from the population of random unlensed event pairs shown in this brown to yellow regions. And furthermore, I'm showing these blue dots, which correspond to promising lens candidates found from Abbott et al., the last lensing paper that was recently posted by the LVC collaboration. So yeah, all these points are shown here, and you can see that there is this one particular event pair shown in the red circle, which is the 1907-31, 1908-03. This is much more consistent with the lensing hypothesis. And if you look at the R-gal which was reported in this paper, it is around 8. And if we calculate the M-gal, considering only the time delays, we also get a very consistent value. But now if we include additional information like the magnification and the phase differences, the M-gal value increases. So this gives more confidence in this event pair favoring lensing. We have also calculated these kind of joint distributions for future detectors, next generation detectors, Advanced LIGO, A+ LIGO, and the Cosmic Explorer and Einstein Telescope. And these results are shown for event pairs of same type or of different types. Overall, we are just trying to make the case that M-gal can offer an improved ranking statistic. It is much more useful to consider the joint distributions rather than focusing only on the time delay. So next, I want to talk about microlensing. So far, I have been talking about lensing by individual galaxies. So in the context of gravitational waves, we are looking at the scenario where the wavelength of the gravitational waves is much smaller than the masses of these galaxies or galaxy clusters. But there is also a possibility that one can see lensing by stars or stellar remnants or dark matter. These are the scenarios where the wavelength of the gravitational waves is going to be comparable to the masses of these lenses. And here the diffraction and interference effects are going to be much more important. So if we are talking about strong lensing by typical galaxies, the relative magnifications that we are going to find are going to be a constant factor, whereas when considering these lensing by these low mass lenses, we are expecting to see frequency dependent amplification as shown here by the orange waveform compared to the blue waveform. So the main purpose of this project here is to understand the effects of microlensing effects because of realistic stellar population. So if you have a lensing galaxy and you can see these macro images which are formed around these lensing galaxy, then some of these lensed images are much closer in a higher stellar density environment compared to some of the other images. And the presence of these stellar population or compact point mass population is going to further affect and cause lensing distortions on top of the lensing effects that are seen because of the macro model from this lensing galaxy. So we want to understand
5 more minutes, Anupreeta.
Okay, thanks. So in order, so our goal is to understand the effects, the microlensing effects coming from these realistic stellar populations, the realistic environments that will be around these macro images, and to understand which factors are going to be the most important when studying microlensing effects. Also, whether we will see microlensing effects in the current generation detectors. So we have considered we have done this calculation for type 1 and type 2 images separately, and we are considering them in different microlens density environments along with different macro magnifications which are found for these individual type 1, type 2 images. Overall, what we find when we look at the amplification factors as a function of the frequency is that the distortions are much stronger at higher frequencies, and the type 1 images overall tend to be amplified because of microlensing, whereas the type 2 images overall suffer from de-amplification because of microlensing. We also then consider other scenarios where we either fix the macro magnification and only vary the microlens density, or we fix the microlens density and only vary the macro magnification to understand which of them have much stronger influence on the microlensing. Overall, we find that the scatter due to varying microlens density or varying magnifications increases by increasing the values of these parameters, but between these two parameters, we find that the change in the macro magnification leads to a much stronger effect in the microlensing. And so the macro magnification or the strong lensing magnification of these images is a much more important factor in how strong the microlensing effects we will see. I also wanted to show quickly some of the odd cases that we were seeing and what that meant in terms of the kind of microlenses that are distributed around the macro images. So we explored some cases where we saw very strong microlensing distortions as compared to the black curve here, which is more typical. When we look at the spatial distribution of these microlenses around these images, we found that in the cases of typical strong lensing magnifications, the presence of even a low mass microlens was very important and caused very strong distortions. But as you looked at more and more highly magnified images, the importance of any individual microlens gets diminished, and we tend to see more collective effects from various microlenses in producing these distortions. You can see more information in the poster by Anuj Mishra on this topic, and he's also attending in person, so you can meet him and learn more about this project. I also quickly want to talk about some ongoing work along the similar lines, where we are asking the question, what is the probability of seeing microlensing effects if there is a strongly lensed gravitational wave event in the data? This is really important to know because we want to understand how much these microlensing effects are going to affect even the detectability of strongly lensed events. So for this purpose, we took the mock sample of realistic lenses from a recent paper. And here we are showing the distribution of quad lenses as a function of the stellar density and the strong lensing magnification. And we are showing all the 4 images that are formed in a quad system with different colors. And from this sample, we have drawn 50 lenses shown with the olive points and olive green color points, and these 4 magenta points here. And for each lenses, we have drawn 50 realizations and calculated the microlensing amplification. We then further go ahead and calculate the match between an unlensed waveform and a microlensed waveform to find out how similar or how dissimilar they are. And so this is our preliminary findings. I'm showing here the match between the unlensed and the lensed as a function of the total mass of the binary, and also as the mass, as a function of the mass ratio. So these different colors are for images 1 and 2, and here various curves show the various realizations for each lens system. And overall, what we find is that so in this analysis, we are mainly focusing on the cases where the strong lensing magnification is less than 10, which means we are looking at typical magnification or typically magnified systems. And what we find is that in all of these cases, the match is better than 99%, which means that the strongly lensed systems which tend to have magnification less than 10, they will not be affected significantly because of microlensing, and so their detection is not really going to be a problem. And also, most likely, the parameter estimation for such cases is going to be have very little bias. Going into the future, we want to study the high magnification systems where we expect to see stronger distortions. And then we also plan to do detailed investigations to study how the detectability or the parameter estimations are affected because of these strong magnification cases. Lastly, I just want to show this acknowledgement slide. Since we were supported by various resources from the LSC, LVC, LVK collaboration. So that's all for today. Thank you for attention.
Great, thank you, Anupreeta. Very impressive. So do we have any questions? I guess maybe let's first ask if there are any questions from the people who are present there in the room.
Yes, sir, there is a question.
Yeah, please go ahead.
Fine, Anupreeta, thank you very much for the wonderful talk. I wanted to ask about the last slide which you showed, where you calculated the probability of distorting the waveform enough that it would not be sensitive. So does this probability include the distribution of stars in galaxy? I might have missed that part. So do you consider how the stars are distributed, stars and other microlensing sources are distributed with radially in the galaxy?
Hi. Oh, yeah. So we are considering realistic populations of stars in the galaxy. I need to check what kind of radial distributions we are using. If I remember correctly, we are assuming a Sirsic density profile for the stellar population. And otherwise, we are considering the initial mass function like the salpeter, which is typically used. And yeah, many other parameters are considered while determining the properties of the microlens population. So does that answer your question?
Yeah, it does. Thank you. And I just had a quick follow-up. So typically, how many microlenses would a wave interact with when it goes through the galaxy? Like maybe considering a typical impact parameter, is it one or is it much more than one?
Yeah, so that would depend on the masses of the microlenses. So if we are talking about very low mass microlenses, let's say less than 1 solar mass or something, then they can be in hundreds. If you're talking about much more massive system, much more massive microlens, then it could be a handful or even one, depending. So it depends on the mass of the microlens.
Okay, thank you.
There is a further question.
Great. I think we are out of time. So let's, I hope there are other ways of asking questions like Slack or something. So let's maybe use those. Thanks, Anupreeta, again for the talk. I guess our next speaker is Lankeswar Dey. I'm not sure if he's giving the talk in person or.
Yeah, so he's giving in person.
Okay, yeah. Yeah, okay, great. So Lankeshwar, you have 12. Can you hear me, Lankeshwar?
Yes, I can.
Okay, great. You have 12 minutes to speak. I'll give you a 2-minute warning in the 10th minute. Okay.
Okay, thanks.
Okay, go ahead.
Good afternoon, everyone. My name is Lankeswar Dey. I'm a PhD student at TIFR Mumbai. And today I'll be talking about PTA signals induced by gravitational waves from spinning supermassive black hole binaries in relativistic eccentric orbits. And this work is done with Suhani Gupta and Kumar. So let me give a very brief introduction to gravitational waves. Most of you already know this. So gravitational waves are ripples in the curvature of space-time, and they are generated by accelerating masses. Like in this animation, you can see gravitational wave is produced by a binary black hole, and you can see the ripples in the space-time. So when a gravitational wave passes through an object, the object gets tidally deformed, and the actual exact way how the object will be deformed depend on the polarization state of the gravitational wave. And in GR, there are two polarization of gravitational waves they are allowed. There are plus and cross polarization. And how does this two polarization affect the objects is shown in this animation. Okay, so if you put a ring of particles in a circle on the screen, and if a gravitational wave passes perpendicular to the screen, then the ring of particles should be deformed in this pattern. For plus polarization, it will be deformed in this pattern, and for cross polarization, it will be deformed in this pattern. And the amplitude of deformation is given by the gravitational amplitude or gravitational strain, which is usually denoted by H. So H is basically delta L by L, where delta L is the deformation in length L. Now, different astrophysical and cosmological processes can produce gravitational waves in a vast frequency spectrum, ranging from femtohertz to kilohertz, and different gravitational wave observatories is sensitive to different part of the spectrum. Like here you can show in the high frequency, like order of 100 to 1000 of hertz, the ground-based interferometers like LIGO, and they are sensitive, and the space-based interferometer like the planned LISA, that will be sensitive to millihertz gravitational waves. And another ongoing experiment called pulsar timing arrays, and that will be sensitive. That aims to detect gravitational waves with nanohertz frequencies. And for different these different frequencies, the sources are also different. But in this talk, I will be focusing on this pulsar timing array and their detection of nanohertz gravitational waves. So, as the name suggests, pulsar timing uses pulsars. So, what are pulsars? I think most of you know, but pulsars are highly magnetized rotating neutron stars. They emit beam of radiation most probably along their magnetic axis. And whenever the beam of radiation crosses through our line of sight, then we see a pulse, like you see in this beautiful animation. And the pulsars have very stable rotational period. So we can actually track the rotation of the pulsar by measuring the arrival time of those pulsars, which we call EOS. Okay, and especially the millisecond pulsars, their rotation period are much more stable, and therefore we can, if we detect a pulse, we can very accurately predict from a pulsar timing model when a particular pulse will arrive. Like here in this figure, you can see like the emission of pulses, and there the pulse period is nearly constant, or if there is a derivative, that is also well known. So you can actually predict when a certain number of pulses will arrive. But if there is a gravitational wave which is passing between the pulsar and the Earth, then the passing gravitational wave will change the time of arrival of pulses and from the predicted values. And the difference, the actual difference between the actual arrival time and the predicted arrival time, that is called the timing residual. And in pulsar timing array, we actually look for this timing residual. So let me show a better way of explaining pulsar timing array. So in pulsar timing array, we observed a bunch of millisecond pulsars at different sky location. So here you can see this is the Earth, and there are many pulsars, especially millisecond pulsars, which is located across the sky. And we observe the arrival time of pulses from different pulsars. And if there is a gravitational wave, this arrival time of the pulses from different pulsars will be modulated because of the gravitational waves, and it will create a timing residual. And the residual due to gravitational waves are correlated from different pulsars, are correlated with a quadrupole nature. So this is a very important part for the pulsar timing array, because the residual can also arise from some noise or some DM variations, but the residual arising from the gravitational wave, that will be correlated in a particular nature. So that is very important. So we search for these correlated timing residuals for detecting nanometer gravitational waves. So what are the sources of nanometer gravitational waves? The primary sources of nanometer gravitational waves are supermassive black hole binaries, and the gravitational wave produced by these binaries will be detected by PTA. So as we know that most of the galaxies has a supermassive black hole at their center, and when two galaxies merge, they can form a supermassive black hole binary. Now, it is expected that there are lots of supermassive black hole binaries in our universe which are emitting nanometer gravitational waves. So their superposition of all those gravitational waves will create a background of in the nanohertz frequency. So in this figure, I am showing this kind of a simulation which shows the expected gravitational wave from different supermassive black hole binaries. So here there are lots of supermassive black hole binaries. Only the loud sources are shown by these circles, and all of them add up to form a background. So the background is shown by these different lines. So different lines are for different realization of simulations. So this background will be detected, but more importantly, some sources, their gravitational wave amplitude will be more than the background, and so we say them they are louder than the background. So we can also detect the gravitational wave from those individual supermassive black hole binaries, which is louder than the background. Okay. So for the rest of my talk, I will be focusing on this detection of gravitational wave from individual supermassive black hole binaries. So what are the challenges in detecting gravitational waves from these individual supermassive black hole binaries? So the primary challenge is the effect of gravitational waves from typical supermassive black hole binaries on a pulsar time of arrival is order of tens of nanosecond. Yeah, tens of nanosecond. Yeah, so and the noise level in the pulsar timing, the prediction of pulsar when a pulsar will arrive, that is also order of same magnitude or maybe larger than that. So our signal is weaker than the noise. So to detect with signal which is weaker than the noise level, we need very accurate template to search for these gravitational waves in the PTA dataset. So there are already templates that exist for non-spinning binaries in both circular and eccentric orbit, and we have extended in this work to calculate the template for non-spinning binaries, and by incorporating the spin effect, and we have incorporated the dominant order spin orbit effects. So before we go to the calculation of the template, let us take a closer look how the gravitational wave will change the time of arrivals of the pulses. So if, let's say there is a pulsar with an intrinsic period of p, and the pulsar is observed as r, and if there is a gravitational wave, the observed period will be little different than intrinsic period, and let's say the difference is delta p, and the delta p by p will depend on the gravitational amplitude at the position of pulsar and the gravitational amplitude at the position of Earth. And this H is given by is a combination of H plus and H cross, which are plus and cross polarization, and they also depend on the antenna pattern function, which depends on the sky position of pulsar and the sky position of the gravitational source. Now, if we want to calculate the residual, this is just an integral of H at the pulsar and H at the Earth at different times. So just to illustrate how it will affect the pulsar timing arrival. So let's say the blue spikes give you the if there is no gravitational wave, the blue spikes are the actual pulses which have been observed. But if delta p is positive, then this red is what we will observe, and you can see this is shifted from the predicted value. And similarly, if the delta p is negative, then the pulse will come little before what is predicted. So this is how the TOS will be modified. So to calculate this R of t, this depends on two things. It depends on gravitational waves at the position of the Earth when the pulse reaches Earth, and the gravitational wave at the position of pulsar when the pulse was emitted. So basically, to calculate this r of t, we have to calculate this h at different times. So how do you calculate this h, or the gravitational wave strength? So the h, or h plus or h cross, this strength for two polarization, that depends on r dot phi dot, where r is the binary separation of the source, supermassive black hole binary, and phi is the orbital phase, and r dot phi dots are their time derivatives. They also depend on some angles. Those angles determine the orientation of the orbit on the sky plane. So those are basically given by some inclination angle. But if this is reference plane with the sky plane, then the inclination angle and longitude of ascending node, and also the mass and mass ratio of the binary. So first, let us see how do we calculate r dot phi dot. To calculate r dot phi dot, we use something called Keplerian parameterization. So in Keplerian parameterization, I will not go into detail. So basically, we use something called mean anomaly, which is basically 2 pi by the orbital period. And from mean anomaly, we can calculate something called eccentric anomaly. And from eccentric anomaly, we can calculate the phase and also the radial distance that can also be calculated from the eccentric anomaly. So once we have this phi and r, we can also take the time derivative to get r dot and phi dot. So this is this is shown for a Newtonian orbit. But if we add the effects of gr, then it will be also different. So we have used this r dot phi dot expression for post-Newtonian accurate Keplerian parametric solution.
Sorry, Lankeshwar, two more minutes.
Okay, thanks. Yeah, so now the r dot phi dot are sorted out. Now that's angles. Okay, so if the binary, the black holes are not spinning, then the angles or the orbital plane will be constant, remain constant. But if the black holes are spinning, then this angle, the orbital plane will precess, and this angles, this inclination and this longitude ascending node, that will change with time. And also due to the emission of gravitational waves, the orbital period and eccentricity will also decrease with time. So now then the n and e are not constant. So we the angles, now to calculate those angles, you have to use 4 different angles in a particular sky, from go to sky plane to some invariant plane to the orbital plane. So basically, what we have to do to get all those r dot phi dot and also the evolution of the angles, we have to solve 7 coupled differential equation. So those are for n is the mean anomaly, which is 2 pi by p, eccentricity, some argument of periastron, this mean anomaly, and 3 different angles which will tell us the evolution of the orientation of the orbital plane with respect to the sky plane. Now, after doing all this, what we can do now, as we have the time evolution of r dot phi dot and also the angles, we can use the expression of h plus and h cross, and then we can use this formula to calculate the residual, or which is also called the PTA signal. So here I am showing an example of the expected PTA residual for a certain typical supermassive black hole binary for a particular pulsar. And here I have calculated for different spin value of the primary black hole. Okay, so here you can see if we assume different spin values, the gravitational induced residuals look very different. So that means the PTA signal that we get, that actually depends on the spin value, and the spin of the black holes can significantly affect the expected PTA signal. So to summarize, the pulsar terminal experiment aims to detect nanometer gravitational waves coming from supermassive black hole binaries, and there will be 2 kinds of sources. One will be background, and the sources which are louder than the background, that can also be detected individually. And to detect those individual sources, we need accurate template, and the actual template that depends on the spin of the supermassive black hole binary. So when we search for those supermassive black hole binaries, we should consider the spinning supermassive black hole binaries instead of non-spinning supermassive black hole binaries. So thank you very much, and that's all.
Thank you. Thanks, Lankeshwar. Any questions? Yeah, someone has to check if there are questions in the people present there.
Probably a very naive one. So presently, what are the main challenges in order to detect gravitational PTA?
Okay, so the main challenge is basically the signal is lower than the noise. Okay, so we expect, as we have longer and longer baseline, with the SNR, the signal to noise ratio will improve. So currently we use more quality data and for longer time span.
Any questions from people who are participating over Zoom? Maybe I can ask a quick one. Lankeshwar, are these post-Newtonian templates going to be really useful for detection eventually, or would you need numerical templates?
Okay, so for supermassive black hole binaries, they are in the when they emit in nano gravitational waves, they are basically in the early inspiral phase. So we think post-Newtonian will be enough for this inspiral phase detection with PTA. But as we go to higher and higher frequencies, so currently the PTA, the higher band is around 100 nanohertz, but the LISA will detect the merger of supermassive black hole binaries. Maybe for that we need numerical relativity. But for PTA, currently post-Newtonian is accurate enough.
Okay, excellent. Really nice. Thanks. Any more questions? Yeah, go ahead. I can't see anyone.
Thanks, Lankeshwar, for the nice talk. So my question is, so there are two kinds of sources that we can take using PTAs, right? And you're talking about the ones which are just single source.
Yes.
So so presently, most of the PTAs are focused on the background detection.
Yes.
So is there more challenge in the single source detection, or is there some other reason?
Okay, so most of the people are focused on detecting background because we expect we will first detect the background because it is for a long frequency range we can get the power spectrum. So detecting background is easier because it involves less number of parameters also. But detecting for individual, it is first of all very computationally expensive. Even for circular orbit, it is very computationally expensive. If we include eccentricity and if we also include spin, then it becomes very computationally expensive. So people think that at first we should go for background, but there are parallel efforts. There are already like different PTAs have put strings constants on individual sources also. So it's not just background. People are also parallelly focusing on individual sources.
That makes sense. Thank you.
Okay, great. Yeah, I think we are out of time. So thanks, Lankeshwar, for a nice talk. Our next speaker is Souvik Jana. I think he's also speaking in person. So maybe if you could get set up. So Souvik, can you hear me?
Yes. Yes.
Okay, great. So you also have 12 minutes to speak. I'll give you a 2-minute warning in the 10th minute. Okay.
I guess I'm audible.
Yeah, you're audible. Did you hear me?
Yes.
Yeah. Okay, great. Go ahead. Yeah.
Hi everyone, I'm Souvik Jana, grad student at ICTS. So I'll be sharing our results from our work concerning cosmological parameters with strongly lensed gravitational wave events. So the work is near completion. The work is done in collaboration with Saswat and Ajit at ICTS and the UCSD. So gravitational waves are completely new window onto the universe, and so far 100 GW signal detects have been already detected. Those are from the compact binary coalescence, and also also it is expected within few years 1000 GW events and will be detected. And with the 3G detectors, third generation detectors, Cosmic Explorer and Einstein telescope, millions of GW events per year is expected to be detected. And so far, most of the source are the BBH, the binary black holes. Gravitational lensing. So while gravitational wave traveling from the source towards the detector, they can be deflected by the intervening mass distribution, mostly by the galaxy and galaxy clusters. So the probability of the lensing is very small, of the order of 10 to the power minus 3. So 1 in 1000 GW events is expected to be detected, lensed. So with 1000 within few years, with 1000 GW detections, first detection of lensed GW signal is expected, and with the 3G detectors, third generation detectors, with the millions of GW detection per year, so 1000 lens GW detection per year is expected. So then that will be a completely new data set, and it will be a completely new probe to astrophysics and cosmology. So our work is proving cosmological parameters using the time-delay distribution of strongly lensed GW events. So some cosmological parameters are well constant from the CMB at a high redshift, and other astronomical observation probes lower redshift. So probing the intermediate redshift would be of considerable interest. By intermediate, we consider redshift up to 15. So GW strong lensing could be one means of doing so. Strong lensing of GW produces multiple copies of the same signal, and those signal arrives to the detector at different times. So there will be a time delay between the lens signals, and this time delay can be accurately measured. And this time delay contains the imprint of the cosmological parameters. So we try to infer the cosmological parameters from this observed time delay distributions. So this is the expression for the time delay. Sorry for the mess. I made it for transitions, but PDF is present. So okay, so the time delay expression. Let's say we have a source at a redshift ZS and a lens at a redshift ZL. So the time delay between the two lens signal is given by this expression. So this expression here, this SIS is a singular asymptotic sphere. This is a lens model we are considering. So it depends on the this box quantity. Contains the information of the cosmological parameters. So this D denotes the angular diameter distances. So DL is the distance to the lens, and DLS is the distance from lens to source, and DS is the distance to the source. So cosmological parameters, and it also depends this ZL is the redshift of the lens. So the time delay distribution will depend on the redshift distribution of the lenses, and it depends on the ZS, the source redshift. So the distribution also depend on the redshift distribution of the sources, and then it depends on this sigma. This sigma is the line of sight velocity dispersion of the lens. So it has a one-to-one relation with the mass of the lens. So the time delay distribution also depends on the mass distribution of the lenses. And this Y is the impact parameter of the signal. So this Y is a number when we are considering Y should be less than 1 to be strongly lensed. So this time delay distributions is a functions of few things. Just so first one is consider the redshift distribution of the sources. So this redshift distribution of the sources can be obtained from the unlensed GW detections. So we are expecting millions of GW detections. So from there we can construct the redshift distribution of the sources, and the shape of the distribution also will be well constant by then. And also this redshift distribution of the lenses and the mass distribution of lenses can be obtained from the Helmholtz, considering some Helmholtz functions. And for impact parameter, we are using uniform distributions between 0 to 1. So this time delay distribution is a function of three independent things. First thing is the cosmology, and second one is the Helmholtz functions, and third one is the redshift distribution of the sources. So there are three independent degrees of freedom. So if we want to infer the cosmology, we need to assume some Helmholtz functions and the redshift distribution of the sources. And redshift distribution of sources will be obtained by these unlensed events. And these Helmholtz functions, we are using some fitting functions to this. There are two references. So if we plot the time delay distributions for different cosmological parameters, so we are assuming some assume cosmological model as a flat lambda CDM model, and the two parameters, this omega m and h naught. Omega m is the matter density parameter, and in units of the critical density of the universe today, and h naught is the Hubble constant at present. So the left hand side plot basically shows if we change the omega m, how the time delay distribution varies. So if we increase the omega m, the time delay distribution varies towards the right, and for the right hand side plot, if we increase the Hubble constant, the time delay distributions shift towards the left. So we can construct the time delay distribution for each parameter values omega m and h naught, considering some Helmholtz functions and some source redshift distribution. And we call these as template distribution because we will use this to infer the cosmological parameters from the observed data. So this is the Bayesian inference of the cosmological parameters from the time delay distribution. So let's say if we have an n confound BBH merger detection, so we will have n number of this delta t. So there will be a set of time delay. This is our data, observed data. So we want to infer the omega, this omega matter and h naught. So the left hand side quantity we are seeking for, and it the right hand side, the first term is called prior. So what we know priori, and this second term is the likelihood. This likelihood can be so if you have data, this can be calculated from the template distributions that we have already constructed. So in considering independent observations, so this likelihood will like this. So so far we don't have any real lens data, so we simulate the lens data. So to simulate the lens data, we are considering some cosmological parameters. Like I'm considering the cosmological parameters, the omega matter is 0.316 and H naught 67.3. So we call it as a true cosmological parameters, and we also use some Helmholtz function model, fitting function Beharuji, and the source redshift distributions Dominic. So if we use that, we will have some in let's say we sample 50K a time delay sample, so we have 50K observational data, and from that we try to infer the we can see whether it recovers the true cosmology or not. So this is the result from this recovery. So we recover this with the constructed template time delay distribution. So we can see that the omega matter is the recovered omega matter is 0.318 and H naught is 67.9. The true one was at 0.316 and 67.3. So to compare it with the Planck constant of Planck error bar, I just plotted the Planck posterior on top of our result. So the precision from the GW lensing is 3.7%, and on H naught is 2.9%. The Planck has a precision on omega matter is almost 1.8% and H naught 0.62%. So the precision from the GW lensing is not as good as the Planck. But the one thing to notice that the correlation of this omega matter and H naught for the GW lensing and the Planck are not in exactly same direction. So we can combine these two constants and get some better constant on these parameters. So here I show that if we don't have 50K samples and instead if we have 20K samples or 10K samples, then how will be the recovery and also the precision. So you can clearly see that with the 10K, the recovery is this 0.329. So it is a little far from the true cosmology, but if we increase the sample size, the recovery is better and also the precision increases. Now, yeah, the left-hand side plot shows this Planck and GW lensing separately. Now, if we use this Planck posterior on this omega m and H naught as a prior, so here is so that if we combine these two things, so the constant is better than the previous. So the red one is the GW lensing plus the Planck 2018, and the Planck one is the blue. So the constant, so it is a better constant now. So yeah, so to simulate the lensed event, we have used some Helmholtz function. So let's say I have used some. So this dV is nothing to do with the CMB depolarization. So this D stands for the Beharuji, and J stands for the Jenkins. So if we use the Beharuji Helmholtz function model to simulate the lensed events, and if we use the Beharuji to also construct the templates, then the recovery is perfect and everything is fine. But if we, let's say, use the Beharuji for the simulation, like the mock data, generate the mock data, and Jenkins for the time templates, then we can see the true cosmology is not inside the 95% control. So this shows basically the strongly dependence on the Helmholtz function. So we need to know the Helmholtz functions accurately to constrain the omega these cosmological parameters from this time distribution.
2 more minutes, Souvik.
Thanks. So yeah, if we have the 50K lensed BBH events, we have 2.9% precision on H naught and 3.7% precision on omega m naught. And if we use Planck as a prior, so 0.4% precision on H naught and 1.2% precision on omega matter density parameter. And also we know that this H0 can be well constant, will be well constant from the low redshift probe by other astronomical observations, and also from the GW observations. Also 2.2%. So if we fix the H naught in our case, so there will be 2.2% precision on the omega m naught. So that is almost comparable with the Planck. So also we have seen the strong dependence of the Helmholtz functions in our for this for the time distribution. So we can flip the problem, fix the cosmology, and probe the different properties of the lens. So that will be direct probe to Helmholtz functions. So this work we are considering, and this is work in progress. So I'll stop here and thank you everyone for listening. If you have any question, ask me.
Thanks, Souvik. Interesting. So I guess maybe I can ask a quick first question, which is that you talked about the problem with the halo mass function. The ideal thing, of course, would be that you don't fix either the cosmology or the halo mass function and infer both simultaneously. Have you tried to do that?
No, actually, we have seen that the variation with respect to the Helmholtz functions and also the variation on the cosmological parameters. We have seen that the variation is a little small. It is this Bayesian method is capturing those things to probe. But if we let them both vary, so yeah, we can constant. But I think there will be the error bar will increase.
That's right. Yeah, the right thing would be to constrain both and then marginalize over all halo mass functions preferred by the data, right?
Yeah.
Anyway, yeah, we have a question from Surud. Go ahead, Surud.
Yeah, hi. Thanks for the talk. I had a similar question to Girish's. In fact, these Jenkins and the Beruzzi et al. Mass functions, they are related to halos defined in different ways. So have you accounted for these differences when you computed the predictions, like, or is the sigma mass relation or sigma SIS mass relation the same?
No, actually, yeah. So depending on the halo mass functions, the sigma will also change. So some extra slide so okay, so this sigma also change. So if we so that's why these biases are occurring.
No. But what I'm asking is the relationship between mass and sigma. Does that remain the same between Jenkins and Beruzzi?
Okay. You are saying that this
because they are defined in different ways.
Yeah, I'm incorporating that. You are saying basically the mass definition to identify the halo, right?
Yes.
Yeah. So yeah,
I think Jenkins was FOF, right? Friends of friends. So
yeah,
the
Beruzzi, this was esovarial.
Right. Yeah. So both are not the same, and so the relationship should change. Yes, because otherwise it's just a matter of labeling, so it should not matter. My other question was whether you have thought about how the SIS distribution changes. I mean, if you consider something like SIE, because with Anupreeta we saw that things change quite a bit. Right. And so, yeah, that would be a bigger systematic, I suppose, right?
Yes, so I have done, but I'm not the full study of regarding this mass model. So I have some. I tried to plot these distributions for both SIE and the SIE. So yeah, is that for the SIE and SIS there are some intrinsically different distribution, not like the small variation. So I think that will be well constrained by just looking at the time distributions.
Okay.
So within the error also HMF introducing also the redshift distribution, everything. Then also these for SIE and SIS they will be completely different. So we can constrain.
Right. Yeah. I mean, whether it's SIE or SIS, that will be simplest to find out. Okay. Thanks.
Great. I'm afraid we have to move on now. So thanks, Souvik, for your talk. And our next speaker is Suhani Gupta, who is speaking over Zoom now. So
hello, am I audible?
Yes, yeah.
I can't share my screen because
I just unshare the screen.
Okay.
Can you please try now?
Yes. Can you see my slides?
Yeah, we can see your slides. We can also see your pointer. Yeah.
Okay. So good afternoon, everyone.
So, Suhani, you have in 12 minutes to talk. I will give you a 2-minute warning in the 10th minute. Okay.
Okay.
Yeah, go ahead.
Good afternoon, everyone. So first of all, I would like to thank the organizers for giving me an opportunity to present my work in front of you all. My name is Suhani and I'm a PhD student. So here I will present my work on halo mass function as a cosmological probe to test the theory of gravity. So first, the Einstein's theory of general relativity, it forms the basis of the theory of gravity and also the foundation of the modern cosmology. So since its inception, the general relativity, it has passed many tests, both in weak field and in strong field regimes with flying colors. It also explains our early universe from the CMB epoch very well. And also the lambda CDM standard cosmological model, it provides a very good numerical fit to many of the observations. Still, we consider the possibility of modifying the theory of gravity. So mainly because of these reasons. So first, as I said, that GR is very well tested in many regimes, but still there are many regimes which are not yet tested for GR. For instance, the intermediate length and time scales. So instead of extrapolating the theory of general relativity to these regimes, we can consider a possibility of a more general theory of gravity, of which GR could be a specific case. Secondly, it has been proven from numerous observations that our universe is expanding at an accelerated pace, and there is no known physical phenomena that explains for this very non-intuitive physical process. So in lambda CDM, we have the lambda, or the cosmological constant, that explains for this cosmic acceleration. But since the cosmological constant, it hovers many theoretical inconsistencies, we are skeptical about it, and many modified gravity theories will actually come up with solutions to explain for the cosmic acceleration. Also, under the umbrella of GR, our universe is dominated by dark matter, which explains the stability of large-scale structures, and dark energy that explains for the above-mentioned cosmic acceleration. However, years of dedicated research and experiment to detect these quantities, we are still completely oblivious to the nature of these two components that dominate our cosmic configuration. So all these factors and many more, they persuade us to go beyond the present theory of gravity and consider some or the other modifications to it. In my work, I'm considering the modified gravity theories in which which explain the cosmic acceleration without invoking the cosmological constant. So namely, I'm working with two modified gravity theories. First is F of R gravity, in which we consider the possibility of interactions between scalar field and matter. And these interactions are encoded in an additional term in the Einstein-Hilbert action, which is the function of Ricci scalar, hence FR. And I consider another theory, which is novel branch of the Wali-Gavadadze-Porati or NDGP gravity model, which considers extra dimensional scenarios in which our favorite 4-dimensional Minkowski spacetime, it is embedded in a 5D bulk, and gravity, unlike other standard forces, it propagates to other dimensions, giving rise to additional degrees of freedom and hence a fifth force. So both these modified gravity theories, they tend to enhance gravity if we compare it with GR, and as a result, they also lead to a boost in structure formation when compared to the results of lambda CDM. So here, to quantify the structure formation, I'm comparing the sigma, which is basically the amplitude of fluctuations obtained for the two variants of the FR gravity I consider. I will tell more about it later. And I compared with the lambda CDM result, and here I compared the NDGP variants with the lambda CDM. So here I see the dark panel, the darkest panel is redshift 0. And as the colors, the light becomes lighter, we go to higher and higher redshifts. We see that for FR, this growth enhancement is dependent both on redshift as well as the scale, whereas for NDGP, we see only that the enhancement is dependent on the scale, on the redshift and not on scale. So for my work, I have used the dark matter halo catalog that is generated using dark matter n-body simulations. We considered lambda CDM, two Husavitsky form of F of R models. The two variants are F6 and F5. F5 deviate more from lambda CDM compared to F6, and two NDGP model variants, NDGP5 and NDGP1. Here again, NDGP1 deviates more from lambda CDM compared to NDGP5. So as I said, that we have very strong constraints on the theory of gravity, and we need to get GR in the regime that it is very well tested. So most of the modified gravity models that we work with, they are supplemented with something called as screening mechanisms, which, as the name suggests, screens the fifth force in the regimes that it is tested, in the regimes where GR is well tested. So here, Husavitsky FR is supplemented with chameleon screening, and NDGP is supplemented with Weinstein screening. And we have 5 independent realizations of each of the models that we are using at redshift 0, 0.3, 0.5, and 1. This is a good regime. This is a good redshift regime because most of the modified gravity signatures that we expect are in this redshift regimes. So coming to the main topic of my presentation is the halo mass function. So halo mass function is basically the co-moving number density of halos in a mass interval for a given redshift and cosmology. So halo mass function, it can be directly measured from simulations as it is a number count, and it can be observationally estimated using tracers of the underlying density field, which are galaxy clusters. So galaxy clusters, they are the largest known gravitationally bound objects in the universe, and their evolution across epochs can actually help us to constrain the theory of gravity. So here in the top panel, I have plotted the halo mass function as a function of mass, and in the bottom panel, I have compared the halo mass function results for the modified gravity models that I use with the lambda CDM results. And here, and this is for redshift 0. And here I can clearly see that all models, they show a very distinct departure from lambda CDM. Hence, we can expect that halo mass function can provide us with modified gravity signatures. So the modern formalism of halo mass function was proposed in the work of President Schechter in 1974, where HMF is given in this form. Here ρm is the average matter density, m is the mass of halos, f sigma is basically halo multiplicity function that encodes the non-linearities associated with halo collapse. And sigma, as I mentioned previously, it is basically amplitude of fluctuations. It is the variance of the underlying Gaussian density field. So we can express the length scales not just in terms of physical entities like mass or radius of a halo, but in terms of the statistical entity sigma also. So why we can make this substitution? We can make this substitution because we can clearly see here that mass and log sigma inverse terms, they are monotonically related, and this relation is dependent upon the redshift. And this switching of the scales also has an impact on the halo mass function. So here on the left panel, I have plotted the halo mass function as a function of mass, and I can clearly see that that there is a different trend at each redshift. And this we would expect because as time elapses, number of structures in the universe would increase. So we would expect that halo mass function would be more at lower redshifts. And when we replace the mass scales, the length scales from mass to log sigma inverse, as I mentioned previously, so we can see that this explicit redshift dependence, which we see here, is somehow approximately eliminated. This happens because the sigma term, it encapsulates the redshift dependence. Here I have expressed the halo mass function in terms of f of sigma. The relation is equivalent. So the main thing to note over here is the universal nature of halo mass function. And this universal property has actually prompted many authors to come up with different fitting form for the halo mass function. They're advantageous in a sense that you do not need to run simulations every time to compute this quantity. And in my work for theoretical comparisons, I have used one such fitting function proposed by Schitt, Moe, and Torman in 2001, here represented as SMT01. So this has been studied very well for lambda CDM. So I studied this even for the modified gravity models that I've seen, and I see a very similar trend. However, we did some tests and we found that the theoretical models, they do not capture the nonlinear dynamics as well as the screening mechanisms that are invoked in these modified gravity models. So this prompted us to adopt a different approach. So what we did is we compared the halo mass function for the modified gravity models that we obtained from simulations with the results for the lambda CDM. So we see here that for all models at all redshifts, the trend is very different. However, we performed again a similar exercise of expressing the length scales not in terms of mass, but in terms of log sigma inverse. And we see here that the explicit redshift dependence that we see here is somehow eliminated. Here, this is for F5, this is for F6. Similar results we also see for the NDGP variance. However, we needed to perform an additional rescaling of the fluctuation scales in NDGP. So using this universal property of the ratio of the halo mass function, we could come up with analytical expression for the modified gravity halo mass function. We say that the modified gravity halo mass function, so for example, we have lambda CDM simulations. We can compute the halo mass function from those simulations for lambda CDM. And then if we multiply it with the fitting function delta NG, we can get the modified gravity halo mass function for those simulations. So as we would expect, this delta NG term would depend upon the modified gravity variant that we're considering. So for instance, for FR gravity model, I have the Gaussian fitting function where parameters A, B, and C, they are the parameters of the fit, which depend upon the FR variant. Here, the black solid line represents this fit. And in the bottom, I have compared the modified gravity halo mass function, which I obtained from this method, with the actual simulation results. And we found that the results are within 5% in the trusted regime. Even for the NDGP case, we have here an arctan parameterization. Again, PQRS.
2 more minutes, Suhani.
Again, PQRS are the parameters of the fit. And we again see that the agreement is within 5%. So to summarize, I have studied the halo mass function in lambda CDM and modified gravity models, namely FFR and NDGP, using dark matter and body simulations. We found that the ratio of the modified gravity to lambda CDM simulation is universal across epochs, and this helped us to come up with analytical expressions for the modified gravity halo mass function. So our main input in our work is the lambda CDM simulations. So this has two advantages. First, compared to modified gravity simulations, lambda CDM simulations are quite inexpensive and less time consuming, and we very well understand them. And secondly, because we are using simulations, so the inherent nature, non-linear nature of structure formation is automatically encoded in our results. And thank you for your attention, and I would be happy to take some questions.
Great, thank you. Thanks for finishing in time. Do we have any questions, either over Zoom or in person? Maybe I can ask one before people make up their minds. What data do you have in mind, Suhani, for measuring the halo mass function?
So in our results, we are confined to using simulations, but like you mean the observation data?
Mm-hmm.
So
eventually, what data sets would enable constraining these models using halo mass functions?
So mainly the weak lensing data, which I'm not working with, but my supervisors are. So we wish to implement them, our results over there. So basically, we want to build up on the halo model formalism for these modified gravity models. So we expect to use this data in that.
Okay, great.
So
we have a question. Sorry, yeah.
So mainly for the LSST data, we expect to use it.
I see. Okay, great. Thank you. We have a question from Surud. Go ahead, Surud.
Yeah, so just to follow up on that. So when you say weak lensing data, you're thinking about something like cosmic shear or combining like galaxy cluster abundances with the galaxy-galaxy lensing signal or the cluster lensing signal?
So like as far as I understand, we wish to use it for clustering measurements and merely to come up with nonlinear matter, studying the nonlinear clustering and matter power spectrum.
I see. So in addition to the mass function, you are also doing studies of the clustering of matter and how it changes in FFR theories?
Yes, I am right now studying the halo bias formalism in these two models.
A halo bias. Okay. Yes. Okay. Yeah, thanks. Thank you.
Great. Any more questions?
So there are no more questions in the room as well.
I see. Okay, I guess I had one more question then, Suhani. Your F of R models show that the sigma relative to the lambda CDM is sort of, it increases towards smaller halo masses, right?
Yes, yes.
So, I mean, I think, have you considered looking into things? There are small scale structure measurements from things like the Lyman alpha forest. I imagine they should be really sensitive in ruling out these FFR models. Have you looked into those at all?
No, as far as I have not looked, but this plot was the linear theory, so it does not invoke screening mechanism. So I think we would need to. So I'm also working on studying the sigma relation, actually the non-linear proper sigma relation, by incorporating the screening mechanism. So maybe then we can think of something relating it with small scale observations.
Right. I guess a corollary to that would be, it might also be useful to see if the dwarf galaxy counts from experiments like LSST would be useful for these FFR models, because you need smaller masses, yes, apparently, and these experiments will detect those. Right.
Okay, maybe I can discuss this with you. Okay, thank you so much.
Any more questions for Suhani? Okay, looks like not. So Suhani, thank you for your talk. And we can move on to the last speaker of this session. It's Tathagata Ghosh. He's speaking in person. So Tathagata, again, you have 12 minutes to talk, and I'll give you a 2-minute warning in the 10th minute.
Okay.
Yeah, go ahead.
Hi, I'm Tathagata from IOCA. And as the title suggests, that I am talking on the simultaneous inference of neutron state Cauchy states and Hubble constant from the gravitational wave emitting from binary neutron stars. And for this work, I'm collaborating with Hashko and Shkat. Yeah, so let's start with a brief introduction in the context that how H0 is estimated from gravitational wave. So for the bright sidings like GW17 or 17, where the EM counterpart has been observed. So in that case, the GW observation provides a luminosity distance directly, and
the independent EM probe also gives the redshift. So in this context, the H0 can be estimated assuming some cosmology. But in case of dark sirens, where there is no redshift information due to the absence of EM counterpart, in those cases, what we have to do that traditionally we consider all the galaxies within the localized region of the GW event. There are some of the sky plots of the GW events from O2 data. And within this localization region, we consider the potential host galaxies and take the redshift of those host galaxies as a prior of the redshift. And with this prior, we can estimate the H0, provide as we have also the luminosity distance estimation from gravitational-wave. So there's a traditional method to estimate the H0. There's an alternative way to estimate the redshift of the GW event, especially for binary neutron stars. So it is first proposed in 2012 PRL paper that's by Chris Messenger and Justin Reed. So by breaking the mass redshift degeneracy. So what happened? Suppose there's a binary neutron star source at redshift C and mass M1, M2, and the tidal deformity lambda 1, lambda 2. So when we detect the gravitational wave event for that binary neutron source, so for the gravitational wave event from binary neutron, in the first term there's a two term. One is PP, that is point particle, and there's another term that is tidal effect. So the PP has the lambda 1, lambda 2 only contributed in the tidal effect. So when the source is detected, as I mentioned earlier, the distance is redshifted. That is comoving distance times 1 plus z. Similarly, the mass is also redshifted in the detected frame. However, the lambda 1, lambda 2 that is comes from the tidal phase term is invariant under the redshift transformation. So that what happens, that is lambda, we can have a lambda is only a function of now source mass if we have the information of the equation of state. So if we know the equation of state precisely, then we can estimate the lambda as a function of m, and lambda 1, lambda 2 can be directly plugged by the GW event. So essentially we have the information of the source mass. And on the other hand, the observed mass can also has been estimated from the GW event. So by comparing the observed mass and the source mass, we can have the redshift. However, the main challenges in this work is that we have to know the equation of state precisely. So in this context, I just want to mention what equation of states we are using. So firstly, I want to mention that we are not claiming that this is the most sensitive to this equation of states. We consider equation of states to demonstrate our method. So we can estimate that US will be well constrained by the third generation detectors like Cosmic Explorer and Einstein telescope, but we can't expect that we know the exact equation of state. So we incorporate uncertainty in US parameters, and we use hybrid nuclear plus piecewise polytrope US model. I referred to two papers corresponding to this model. So the main take-home message from this is we use the equation of state model with 7 parameters, which is shown here by epsilon. The first 4 parameters are the nuclear physics informed parameter, where it is only applicable for the low density region that is defined by 1.25 times nuclear saturation density. But for the higher density of the neutron star, we modeled the model of the equation of state is by piecewise polytrope parameterization. So we consider these 7 parameters in our work, and yeah. So and we estimate and assume some uncertainty in those parameter space of the equation of state, and we are trying to we are showing that we can estimate the US parameters as well as Hubble constant in the third generation data. So this is our methodology, that is a Bayesian formalism. You can see that the H0 is the Hubble constant and the equation of state parameters are estimated simultaneously for a given GW data, and this is the Bayesian formalism. This term is the GW likelihood term that comes from the GW data. Here we consider the mass pair, tidal deformities, and this luminosity distance, and the other parameters are marginalized. And the pi terms are showing the prior. So for the Hubble constant, we consider the prior of from 20 to 120 km per second per megaparsec. And for the masses and the redshift, we consider enough white prior so that there should not be any bias due to the choice of prior. And in the denominator, there is another term that is selection effect. this effect, this term has to be considered to ensure that the GW likelihood term should be unity if we consider all the events. In principle, all the GW events should have a response in the detector. However, due to the SNR criteria, we can't able to observe all the events. So this term will take care of that. And for our methodology, we assume Lankeswar Dey cosmology with omega m 0.3 and H naught is free parameter, and the luminosity distance is related by the ratio by this relation. To apply this decision methodology, we create a mock GW catalog, and this catalog, in this catalog, we injected several BNS and we take 50 binary neutron stars, and the redshift distribution is uniform in co-moving volume and the source frame time. RZ is the merger rate. So in this work, we do not include any merger redshift dependency of the merger rate. We fixed it. And the distance we consider is from 1 gigaparsec to 8 gigaparsec. And in the true cosmology, we consider H naught equals to 70, and the omega it's already fixed throughout the book. And the mass distribution for this work is from 1 solar mass to 2 solar mass, and it is uniform in the source frame. And we inject 1.8-second binary neutron star signal using Cosmic Explorer. And with this sets of injections, we perform parameter estimation of the source over mass pair, tidal deformities, luminosity distance, and inclination angles. And for this, we used Bellevue pipe, publicly available code for parameter estimation from GW data. And for our work, we choose 3 sets of equation of states priors, because we don't know what will be the exact how much we can constrain the US prior before the third generation observation will start. So we consider 3 sets of priors. The exact values are shown here in summarized in this table. However, from the visualization, you can see that the top panel of the MR plot, where the black line is the injected equation of state, and we show with the shaded region red, green, and golden yellow with a 90% confidence interval, credible interval of the MR plot. And we also mentioned some of the MR plot from observation like radio data and the GW data. So with this equation of state prior and the H naught prior, which is uniform between 20 to 120 km per second per megaparsec, we apply this method to 50 GW events. And you can see this is a corner plot of the 7 parameters of the equation of states along with the Hubble constant. And our injected Hubble constant is 70. So you can see for the equation of state 1, which is well constrained as a prior, we considered. So the equation of state is very well constrained, as well as the H naught also. We also have the similar result for equation of state 2, where you can see this is a well constrained, and all of them are the median is within the 1 sigma interval in all of the cases, and same for the equation of state 3. So when we compared all the 3 results in the same page, so you can see the H naught posterior in the this panel, where you can see that the red that is a posterior 1 and posterior 2, that is correspond to equation of state 1 and 2, is much more well constrained in comparison to equation of state 3, because there's a more error in the equation of state prior. And this is also shown in the top panel, where we show the MR plot obtained from the final one after applying the method to the 50 GW events. So you can see that for the equation of state 1 is more constrained in compared to the equation of state 2, and so on the equation in compared to the equation of state. And the detailed result is summarized in the table. You can also see it from the corresponding paper. So in this work, we mostly summarize that we are able to demonstrate how a population of binary neutron star can constrain the Hubble constant and the equation of state parameters simultaneously in third generation detector era. And it's most important, it will be important this method will be important when the electromagnetic counterpart will not be identified. And we also show another the H naught for the equation of state 1 and state 2 is almost similar. This is due to the fact that the distance estimation is the error in the distance estimation is larger in compared to the error in the redshift. But I want to mention that we consider the 128-second BNS signal. However, in the CE era, we can expect hour-long duration signal. So, but due to the computational expense cost, we didn't consider it yet. But we'll try to incorporate this effect and see how the result changes. And I will stop my talk here. Thank you.
Great, thank you for finishing also in time. Any questions?
Yeah, so there are 2 questions.
Yeah, go ahead.
So nice work. What I wanted to know is that you have considered lambda CDM cosmology.
Yeah, flat lines.
Yeah. So, like, have you thought about using WCDM or other extensions like that?
Yeah, we didn't incorporate this, but we thought to using the more constant H0 prior.
Yeah.
And try to probe the other cosmological parameters like omega m or equation.
Okay, because your value is coming very near to the Planck value.
No, it's a simulation, so we inject it as 70. But when we consider in the data, we need to think about the several cases. But it's a simulation, so you can't say that it's a near to Planck or near to Schroeder.
Thanks. So, can we use the 2017 binary differential merger to test your formalism?
That comes at the redshift Z 0.01. It's very low redshift, so the effect will be very minimum, and I don't think the data quality is too good to estimate that. So it will be good if the event is little bit at larger redshift. So we can test it 04 or 05.
Can give you a constraint, but that will be more broader.
I don't know. I didn't check, but it may give the almost the prior you're using, because it depends on how the mass is coil constraint, the tidal uniformity, and the distance.
Okay. But okay, so previously you were trying to break a degeneracy between the mass and the redshift, but here you have got a degeneracy between the equation of state and the Hubble constant, right?
Just a minute. No, this is circular, so there is no correlation, right?
No, not correlation, but your like Hubble constant.
Equation of states are degenerate, yeah.
No, your Hubble constant measurement will depend on the equation of state and vice versa.
If we consider the universal equation of state, it shouldn't depend. It will give the bias H0 or the bias EOS parameters. I don't get your point.
Okay, we can discuss sometime.
Good. Any more questions?
So, do you have some information about the location of neutron stars for which you are finding the equation of state?
No, the location comes from the GW data.
So, like, how far the neutron star is?
Location means in terms of sky location or the redshift.
So, anything like redshift also will work, or even the patch of sky you are looking for, like how?
The patch of sky comes from the GW data. When you estimate the parameter from the GW data, there's also prior over the sky location. There's also prior. And with the more number of detectors, you can localize it well.
And do you know how far this neutron star is?
It depends on which sensitivity detector you are using, how many distance you can probe, how much distance you can probe. It depends on the which sensitivity you are using in the detector. That is, in the O4 it's around 200 megaparsec. In the CE it will be more than 2 gigaparsec. So it depends.
This equation of state should work for all the.
Yeah, it's independent of the where the VN is. Yeah.
Independent of the location and.
Yeah. Of course, definitely.
Great. Okay. Any more questions?
No, sir, there is no question.
Okay, great. Thank you then, Tathagata.
Yeah.
And thanks all. I'll thank all the speakers, and I will let the people present there clap for all of them. Is that okay? Good. Nice. Bye then. I'm logging off.
Thank you so much.